G'day, lovely people. Okay, today I want to chat about one of the earlier challenges that you're going to get as you're spinning up one of these site reliability engineering or SRE capabilities within your organization. That is, you need to determine the boundary of what it is that kind of SRE needs to care about, and what should be deferred to kind of someone else. Okay, so in my experience, reliability affects a whole kind of range of different aspects of production systems. Things like availability and performance, and the quality of those systems, and whether or not those systems are correct. And finally, kind of machine learning aspects of production. The first one, though, and the one that I think is easiest to think about is just straightforward availability. Okay, so if a system becomes kind of unavailable, essentially what happens is it cannot do what users expect given some sort of reasonable user input. Availability depends across kind of the way the different systems are implemented. There are kind of architectural choices, but essentially, given a kind of well-formed input message, the corresponding output message does not arrive. So let's take the common example, something like an HTTP-based RPC system in which we submit our well-formed request. We might make a GET request for some sort of resource, and the server might respond with something like an HTTP 503 bad gateway. In this case, the system is unavailable. We might take that same system and we might have our client, and the client places that GET request to the server, and the server takes a very long time. So eventually the client just times out. The server is therefore, from the client's perspective, equally unavailable. For something like an event-driven system, that can be a little bit trickier to reason through, but essentially it's still the same. You still have a well-formed input message, something that you write to a Kafka topic or a Rabbit topic or sort of queue, and you don't get the corresponding output across a reasonable time. Okay, so we like to measure availability. Actually, from SRE's perspective, we like to measure everything. Usually we measure availability as a percentage, something like availability is like 100 by 1 less the failed requests over the total requests. That gives us the availability as a percentage, and we can model the availability by looking at that percentage over periods of time. We can then set targets on that period of time. These are usually called service level objectives. For example, we might say that the particular HTTP service, we expect it to respond successfully in 99.9% of all cases, but averaged out over a rolling 28-day window. Okay, so SREs, we care about availability. We also care about performance. The performance of a system is usually measured by assigning some sort of acceptable time threshold for a given operation to complete given a specific throughput. So as a concrete example, we might have our HTTP system from earlier, and we might give that a budget of 100 milliseconds to complete that RPC. Or if we have our event-based system from earlier, we might be a little bit more generous. We'll give that 500 milliseconds for a corresponding event to appear in the output if we supply some sort of trigger event in the input. Systems do not usually kind of sit on kind of one side or another of a particular performance bound. Rather, they approach that bound as the throughput of the system kind of increases until at some point they can't process that throughput, and the kind of time, the average time at any given operation drifts outside that acceptable threshold. So like availability, we like to measure performance, but unlike availability, we tend to measure performance in two different ways. We measure it for diagnostics purposes, and we also measure it kind of for accounting purposes. For diagnostics purposes, it's usually better to measure performance in some sort of histogram-like structure. That is, a structure that kind of puts each request into a bucket of performance. So let's imagine that we kind of get a whole series of requests. Each time that we get a request, we measure how long it takes, and we put it in a bucket of corresponding length. We might have buckets, for example, at 0, 25, 50, 100, and 200, and 400 milliseconds. And if we have a request of something like 18 milliseconds, then we'll put it in that first 18 to 25 millisecond bucket. Correspondingly, if we have another request, even a 700 millisecond request, we'll put that into the 400 milliseconds plus bucket. Okay, so this creates a distribution of requests. this distribution of requests also allows us to kind of reason through the internal state of that system. If we have a system in which most requests are kind of landing in the bucket that is at the boundary of acceptable performance, we usually know that the system is kind of nearing its limit. The system is likely to be kind of stuck or constrained on some sort of bottleneck process, but at this point, it's not actually transitioned into a failure state. We usually just need to scale something, the bottleneck process. Conversely, if we have the majority of requests landing above the acceptable performance, the system is in a failure state, and it's unlikely to kind of recover quickly by itself. We need to drop work and then scale the system in order for that system to recover. More generally, to measure whether or not a system has acceptable performance, it's easier to reason through by measuring just the number of requests that were within bound of acceptable performance versus those that were not. Just like availability. The equation is very similar. It's something like performance is kind of 100 by 1 less the requests that were too slow over the total requests. Okay, so we have availability, we have performance. Let's chat about correctness. Now, a given system might be available, arguably, if we give it an input message, a well-formed input message, and it responds with a well-formed output message. However, a given system can respond with a perfectly well-formed but entirely incorrect response. This can be very simple to reason about, such as let's imagine that we have this system which just sums numbers for some reason, and we give it the two numbers 2 and 2. Subsequently, the system returns us 5. Yeah. If the code does not kind of depend on other code running in parallel, this should be relatively straightforward to figure out, to detect. All we do is we write kind of an amount of test coverage around this code that reproduces that issue, and then we modify the code until that issue is fixed. There is also a second class of issues, the so-called kind of tolerably incorrect issues. These usually manifest in a large distributed system. Let's consider a chunk of this system. Let's consider a system that kind of checks whether or not a given postage, when we need to kind of pick up a package from point A and deliver it over to point B, we might query a whole series of postage carriers and determine how long each of those postage carriers would take to deliver our package, thereby being able to pick the fastest or something. This system might be composed of a central service, let's call it a postage service, which makes requests to different carriers A, B, C, and D. For such a system to have a really definitive answer, all of the queries to all of its dependencies must be successful. However, such a system is only reliable as its least reliable dependency. Let's imagine that we have our C dependency, and that's having some sort of trouble. When the postage service attempts to call this C dependency, it finds that it doesn't work, and now that it can't kind of get a correct response, it therefore marks its own request as an error. At some point in time, all carriers are likely to be unavailable. Additionally, practically we've failed all of our requests just because a particular delivery provider was unavailable. This is a bit of an intolerable business condition. We only need the best possible provider for our business case. Given this, we modify our system such that the postage service gets as many results as possible, but doesn't fail on any specific result. If we have C unavailable, for example, it'll take the results of kind of A, B, and D and do its best. However, we now have a situation in which the request is mostly correct. To measure correctness, we need to measure a couple of different things. To measure binary correctness, the only way in which I can kind of reason this through is we have a system, whatever the black box is. We give that system a defined series of inputs for which we already know the outputs. And we validate that the system produces those outputs when we provide the inputs. This is either just unit testing, end-to-end testing, or if you're executing it in production, probing the system. If you're kind of measuring the correctness here, it's measured in terms of the same way as availability. That is to say that we have correctness is 100 by 1 less the number of failed tests versus the number of total tests. Measuring mostly correct requests is a little bit more challenging. It is possible to measure kind of the total number of requests which have any regression by marking the request with metadata indicating that that regression actually happened, so some sort of HTTP header which indicates C failed, after which we can measure correctness in exactly the same way. That is to say that the correctness is the 100 by 1 less the number of compromised requests versus the number of total requests. However, hundreds of services can contribute to any given request within a large distributed system. At any given time, at least some of these are usually broken. Given this, it's more useful to count specific regressions. Something like the availability of C specifically is 100 by 1 less the failures of C over the total requests. After this, we can measure the availability of A, B, and D in exactly the same way. Invariably, this will create a large number of time series, a large number of ways to look at the reliability of that operation. But it can also allow weighting of the different kinds of regression within an operation so that more important things, something like loyalty data, for example, contribute more to a quality score than the less important things, something like analytics data, for example. Important, but not critical. Okay, so we've chatted about a few things: availability, performance, and data correctness. The next thing we need to think about is data recoverability. Data is a challenging issue because there are many different ways in which data can drift. However, in practice, the most kind of critical challenge to solve is to be able to reproduce production data that would otherwise kind of become corrupted or deleted. There are many, many ways to reproduce different production data. This could include things like reproducing it from an event-based system if it's a materialized view, reproducing it if it's a state snapshot that you store some elsewhere, so a database backup or something, or reconstructing the data from other records of note. So, like everything else, we need to measure our ability to recover data. The only way in which I know how to measure the recoverability of a system is to attempt to recover it, and then validate the recovery of that against the production undamaged dataset. Should the data be consistent, or at least within an acceptable bound, the recovery is successful. An organization's measurement of this, then, is thus the time in any given context since the last successful recovery. So we've talked about availability, we've talked about performance, we've talked about data correctness, we've talked about data recovery. The last and coolest topic is machine learning. There are a number of really interesting reliability challenges associated with machine learning. These are things like making sure that your model is trained on appropriate data and not actually overfit on that data, or making sure that the training data is of high quality and represents what it's supposed to very well, making sure that the input data is sufficiently close to the training data that it kind of models the output and is still predictable, or making sure that the input data, the data that your system is processing in real time, is not maliciously constructed. However, in practice, these can be kind of considered by thinking as the machine learning model as a kind of black box, and then thinking about its inputs within the lens of the other reliability measures, the availability, correctness, performance, and data recoverability. Oh, we've covered a lot. Actually, site reliability engineering is a really broad discipline. However, fundamentally, at least in my experience, the problem that it seeks to solve are relatively clear and consistent across multiple different system architectures. Hopefully this short video kind of explains them and allows you to evaluate your own SRE work against these fundamental challenges. Thank you very much for watching. Please like and subscribe. I'm not quite sure to what yet, but this is kind of a fun hobby. And if you subscribe to something, if you give me some sort of feedback, that will make me feel good. If you think I'm wrong, great, perfect. Tell me in the comments about how much smarter you are, or how much more your idea makes more sense than mine, and I'd be happy to learn. Thank you very much, people, and I will let you get back to whatever you were doing before I interrupted you with this video. See you later.